In Chapter 15, we're going to start looking at regional climates. We'll start looking at what's called the Köppen classification of world climates, which is essentially based on the distribution of vegetation. The Köppen system is based on the vegetation distribution because vegetation has a preferred temperature and moisture range. Köppen therefore translated vegetation properties into monthly mean rainfall and temperatures and annual mean temperatures as well. The main criticism of the system is that the soil and topography also affect vegetation, so it's not just climate that's affecting the vegetation, which you based your classifications on. Also, the temperature and precip and the general climate varies year to year, while plants would lag this greatly. So the other main criticism, it's simply not dynamic enough. However, it's not a bad scheme, and it's used widely. Köppen's major climates, and we'll go through these over the course of chapters 16 through 18. A, tropical rainy climates. B, very dry climates. C, mid-latitude rainy climates with mild winters. D would be mid-latitude rainy climates with cold winters, places like Chicago. E are polar climates, like Barrow, Alaska. Second letter in the climate scheme, F typically means rainy. There's no distinct dry season. W, wet and dry, means there's definitely a distinct wet and a distinct dry season. M means monsoonal, where the dry season is very short. S means Mediterranean, where the summer's dry and the winter's somewhat more wet. Again, we'll get into each one of these as we need to. For me, it's not as important that you know the lettering schemes, it's that you know the mechanisms that cause the climates we're going to look at. Here's looking at basically all the climate types according to Köppen, at least to the first order here, and then you can see there's quite a few of them, so we'll take our time stepping through them. Here they're spread out on a map. Typically in the tropics you have more A's, B's surrounded around there since you have subtropical zones that are fairly dry, C's after that. As you go more polar, you get into the D's and finally the E's in the polar areas. Now H is a highland area, which is just mountainous terrain. They didn't bother classifying different types of mountains or different slopes of the mountains. There's so much variability in climate on a mountain. They just declared all mountains at this scale H. So getting into chapter 16, tropical climates, we're going to look at radiation and temperature, precipitation, the tropical rainforest climate, tropical wet and dry climates, tropical monsoonal climates, the tropical, or really what they're called subtropical deserts that exist in the descending branch of the Hadley cell, and also the coastal deserts, which are the world's driest places, even though they have relatively high humidity values. Radiation and temperature. The intensity of radiation is high throughout the year in the tropics, but the radiation reaching the surface varies within the tropics due to lots of cloud cover. Little seasonal variation in the photoperiod. It's always about 11 to 13 hours of sun depending on the month and how far off the equator you are. There's much stronger diurnal than seasonal cycle in temperature as a result of all this. Wet tropics have the smallest annual temperature range of only 1 to 2 degrees Celsius over the year. So imagine living in a place where the temperature is always pretty consistent throughout the year. So here we're showing the diurnal cycle. There is a change in day to night as the sun goes down for a full 12 hours and comes up for a full 12, but over the course of a year, the annual cycle is pretty damped compared to that. The shading here shows where these places are, where the greater diurnal energy cycle is higher than the annual energy cycle. So since the temperature is pretty consistent throughout the year, what really defines the seasons in the deep tropics is the rainfall, and that definitely has a seasonality to it. Only 10% of the tropics has substantial rain every single month, meaning that it's not that all the tropics have rain all the times of the year. Only a really narrow band along the equator has that. Most tropical regions have a marked rainy season associated with the ITCZ passing over for the most part. The variability in rain distribution leads to deserts, savannas, and also rainforests. So it's not just all rainforest down there. There's a whole bunch of different land surfaces based on the climate that is active in the tropical zone. Here, painted orange, are the AF zones, the tropical wet zones. These are the zones in the Congo and the Amazon where there's decent rain every month of the year. And it includes most of Indonesia, that's also a pretty rainy place, and parts of Central America as well. Tropical wet and dry zones are places that have a definite dry period and a definite wet period. And those zones are shown as kind of beige here, pretty close to the tropical wet zones. They're just far enough though that they're not under the ITCZ all the time. They get brushed by it during a certain season, which gives them their rainfall. Tropical monsoon regions are similar to that, however they have a more pronounced wet season and a shorter dry period than the tropical wet and dry. So H in the Köppen scheme means a highland area. They don't bother defining differences in that highland area because there's just so much variability on mountains. You can get some sense, however, of the highland climates by the climates around them. For instance, these H's over in Indonesia that are surrounded by tropical wet zones. Obviously, these are going to be your cloud forests on the mountains, very rainy mountainous areas in Papua New Guinea as well as parts of Borneo too. So looking at the dominant air masses, the tropical wet zones dominated by a maritime tropical air mass most of the year. The tropical wet and dry, the tropical monsoonal, and the subtropical steppe zone, which is a low latitude semi-dry area, has alternating seasons of maritime tropical and continental tropical air masses. And then BWH here is the subtropical desert, the low latitude dry zone, and that's dominated by continental tropical air year-round. And really what's happening there is the descending branch of the Hadley cell is really drying out the air as it subsides to that zone. Now the tropical wet climate, mostly rainforest underneath it, makes sense. Rain every month with some peak. 7% of Earth's surface is rainforest, where the biggest tracts currently in Indonesia, Peru, Brazil, and the Congo as well. There's a tiny annual temp range here. This is the smallest on Earth due to consistently overhead sun, high humidity with high heat capacity, as we know, and similar day length all throughout the year. As well, if you're in the thick forest at the bottom, you're also protected from a lot of the variation going on in the top of the canopy. Sustained periods of high intensity rainfall. For example, the 24-hour records held here at 73.5 inches of rain in a single day. And that is more than 4 times Boulder's average annual precipitation, to give you an idea of how much that is. Here we're looking in the lower left, Belém, Brazil. Definitely rainforest zone, tipped towards the mouth of the Amazon there. You can see the temperature trend over the course of this year is not much variation at all. That red line is pretty much flat-lined. Somewhere around 85 degrees is the average temperature, including day and night. 1 degree south, so this is right at the equator. You can see they definitely have a maximum amount of precipitation in their warm season, which is January, February, and March. However, every month has substantial rainfall, so they're declared an all-wet region. Singapore as well, they're 1 degree north, so just on the equator as well. They have pretty well spread precipitation with no obvious peak. It's kind of interesting that their maximum precipitation does happen though during December, January, February. However, this is a result of the ITCZ on average being a little north of the equator. So during the equinoxes, you could say it's maybe at 5 degrees north. So during the southern hemisphere summer, it does make sense that the ITCZ would creep down to its maximum southern extent, maybe at the geographical equator or even further, and really give them the hardest rainfall at that time. Again, we don't see a much temperature variation over the course of a year whatsoever. So really what's dominating most of these tropical zones is the ITCZ and how it rocks back and forth, following the path of the sun over the course of the year. So as I said, its average position's a little bit north of the equator. It's attracted most of the hot land masses in the northern hemisphere, but it does cross the equator during the southern hemisphere summer, and then it heads well up north during the northern hemisphere summer, and it takes the rainfall on bulk average with it. It also pushes the high pressure cells, the descending branches of the Hadley cell, with it. So those also have a seasonality where they head north during the northern hemisphere summer and then rock back to the south as southern hemisphere summer approaches. Since the ITCZ is following the warmest temperatures, in other words, it's following summer, that means that the precipitation in the tropical belt is falling during the warm season, during their summer, for the most part. Obviously, there's places that are close enough to the ITCZ year-round, the tropical wet zones, that they're getting precipitation constantly, but you'll always find the maximum happens during their warm season in general. Most rain in this area is delivered by convective clouds that primarily form during maximum heating in the afternoon. Moisture is somewhat consistently delivered by the convergence of the trade winds, the northeast trades in the northern hemisphere and the southeast trades in the southern hemisphere, but it still takes some surface heating to cause enough instability to force thunderstorms. So they really can predict thunderstorms every day in these zones. After noon, you typically will have a bout of thunderstorms that may last as much as 5 or 6 or even more hours. So not unlike what happens in Boulder or Denver during kind of July and August, but on a grander scale with much more moisture and heavier thunderstorms. With all the moisture, fog and dew is pretty common in the morning, at the top of the canopy, within the canopy, etc. Cumulus fill the skies from noon and beyond. This is a cumulus cloud bank looking from a satellite. Transpiration from the trees actually helps form the clouds, especially during the dry season. So during their quote-unquote dry season, it's not that dry, but it's drier than the wet season, the trees are actually scooping up into the root water zone well down when there's still plenty of water. The trees will take that, push it through transpiration through their stomates, and it has been shown in these jungles that they give off enough transpiration to significantly impact the cloud field over them, especially during the dry season when there's not a lot of moisture streaming in from the ocean. These clouds help cool the forest, giving them less heat stress, and so they're kind of taking care of themselves, so to speak. Tropical monsoonal zone, AM, pronounced wet season due to the monsoonal flow. The monsoonal flow, again, is a seasonal wind shift. Typically, it means that during their warm season, air is rising over the land surface, bringing in nice, moist air off the ocean. A number of them tend to be at the ITCZ's north or south limits, which means that it kind of sits there for a long period of time with one long wet season instead of two kind of semi-distinct wet seasons if the ITCZ was passing over you more quickly. So here we see a zone in Myanmar at 20 degrees north. We see a pronounced wet season, right? During their warm season, since they're north of the equator, JJA, June, July, August is their warm season, and that's when most of their precipitation is delivered by a long shot. And then they don't get much rain for another 4 months until it returns again. They do have a little bit of seasonality to their temperature, but still not a whole lot, but certainly more than the tropical wet zone. This zone in Liberia is closer to the equator, so they definitely have less variation in the seasonal temperature, as showed by the red line being pretty flat, but they certainly do have a monsoonal rainfall. So looking back at Myanmar, energy budget-wise, why is it slightly cooler in Myanmar when the sun is highest in the sky compared to 2 months out on either side? I'm asking, why is there a little dip right here compared to the maximums around it? Certainly this is when the sun's highest in the sky, and probably also when you'd have the most accumulation of heat if everything else was considered equal. Would it be a lower sensible to latent heat ratio during this time in the dip? More clouds, higher ground conductivity, higher heat capacity, or all of the above? Of course, it's all the above. Water does just that. If you're having that much precipitation in here, you have to have clouds. And you also have a dominant effect from latent energy over sensible heating. It's also going to add conductivity to the ground, so a lot of the energy is going to go into heating the ground instead of heating the atmosphere, and there's going to be higher heat capacity. Water adds heat capacity. So all the above makes sense to keep this relatively cool during the time where you'd have the maximum amount of radiation coming in. It's likely also that the diurnal temperature range would be smallest during this time as well. The amount of water typically dampens out temperature fluctuations pretty greatly, either seasonally or also diurnally. Tropical wet and dry climate, AW, it's like tropical monsoonal, but a more pronounced dry season. The seasonality, again, is caused by the Hadley cell's annual migration from roughly 15 degrees north to 5 degrees south and back. Sometimes the ITZ is overhead, causing rain, and sometimes the descending branch is no rain. So here in Male, you have just that. You definitely have a rainy season that everybody loves who lives there, and then you have to wait another 6 months. So again, it's just like monsoonal, except when it rains, it doesn't rain as hard, and there's a longer dry season. You can see there's an uptick. It's starting to get warm, 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 and just then the clouds and precipitation move in and kind of break that cycle. Everybody's generally happy to get that because plants are growing, etc., and then the cycle starts itself the next year. In Acapulco, pretty same climate. They have definitely a tropical wet and dry as far as precipitation looking here. They don't have much seasonality in their temperature, and this is likely related to the fact that they're right on the ocean. These are zones where you typically see savannas, especially in parts of Africa. Large migrations of animals are often associated with tropical wet and dry zones. So essentially the animals are trying to move on following the rainfall as it moves with the ITCZ. Next we have subtropical steppe, which is called BSH, similar to the tropical wet and dry, but much less rain overall. So there's a seasonality of precipitation, but overall there's not a whole lot of rain. Further poleward typically, thus limited effect from the ITCZ. These are places right on the fringe of the extents of the ITCZ. They just get brushed by it briefly, and then it goes away for 9 months before it will return again. So they have subsidence most of the year. Most of the year they're in the descending branch of the Hadley cell and high and dry. So this zone in Australia at 21 degrees north, you can see now you're starting to get the seasonality of temperature pretty well. You're closer to the pole, so there's more variation in the solar angle, etc. There's more variation in daylight hours as well, and you do see a seasonality here of precipitation associated with the ITZZ just brushing them during their warm season, which is TGF. Monterey, Mexico, same type of deal. Then you move into zones that are really right underneath the descending branch of the Hadley cell pretty much the whole year long. So these tend to be at 30 degrees north or 30 degrees south. Usually clumped to the west side of the continents due to easterly trades. So easterly trade winds will tend to bring enough moisture to the east side of these continents to keep them out of the tropical desert zone. For the tropical regions, this has the largest seasonal temperature range. Two real reasons there. First of all, the latitude's the highest out of the zones we looked at. Both these zones in Yuma and Cairo at 31 and 32 degrees north, so that's certainly part of it. And also, they're subtropical deserts, they're far from the ocean in general, and so they're continental, which is going to have a larger seasonal temperature range. These zones do have the largest diurnal temperature range on Earth. That's a combination of dry air, maximum amount of daytime heating, because there's dry air, no clouds. At night, you can really cool effectively through long wave radiation due to the fact there's no clouds and there's not a whole lot of water vapor in the air. Also, the sand heats and cools the air very well. So in these regions with really dry sand, not very conductive. All the energy that comes in heating the sand has a hard time conducting into the deeper ground. There's no water to evaporate, so most of it goes into sensible heating. So the air temperature gets quite hot. At night, though, the sand effectively radiates away a lot of its heat to space. And since no heat was stored in the deeper ground during the day because it wasn't conductive enough to get it there, there's no reserves at night to bring it back up from the deeper ground. So you can see not much precipitation in these zones any time of the year, and getting up to a decent seasonality of temperature as well. Now these subtropical deserts are far enough north that they're starting to get an influence from mid-latitudes type cycles. For example, the jet stream. The northern Sahara will get rain during their winter season because that's when the jet stream is farthest poleward. So remember, the jet stream follows the temperature gradient. The temperature gradient heads down further equatorward during the winter, and then it heads northward towards the pole during the summer. So the jet sags south during the winter, and it can clip the northern part of the Sahara with extratropical cyclones associated with the jet stream at that time. So that's when they're going to get their rain, if they get any at all. The South Sahara, on the other hand, you can see the kind of green line down here in Nigeria, the Sudan, and Ethiopia. They're going to get their precipitation during the summer because that's when the ITZZ is going to clip them. The jet stream of storms never get that far south, so they don't have a chance to get winter precipitation. So we can look at those distributions across the Sahara here. Again, we're looking northern hemisphere, so DGF, December, January, February, that's their winter, and that's where all the rain comes on the northern part of the zone. If you're in the middle of the Sahara, you just don't get any rain at all because you're not getting any type of storm. If you're in the southern zone, you are getting the ITCZ and the warm season precipitation. Here's just looking at 23.5 degrees north, the Tropic of Cancer, the Tropic of Capricorn as well at 23.5 south. You see the Great Australian Deserts right under that zone. That's the average position of the descending branch of the Hadley cell, and that's why they're there. You have the Namib and Kalahari deserts in southern Africa here along 23.5 degrees south. In that same type of zone, you have the Sahara Desert, obviously, the Arabian Desert, the Great Indian Desert. All these zones are deserts because they have descending air most of the year. There are some tropical deserts that are a little bit different. More specifically, we can look at the Atacama and Peruvian Desert, where some of it's actually pretty close to the equator. You'd think it would be rainy, but it's very much not rainy. It's the driest place on Earth. So we'll have to look at those mechanisms quickly. So these coastal tropical deserts, they're the least amounts of precipitation in the world, sometimes 10 or more years with no rain at all. They're found on coasts downwind from cold water offshore. They're found west coast of Africa and west coast of South America. Baja would also be considered one, the west coast of North America, but I would say the Atacama, Peruvian, and Namib deserts are the driest by far. Cold water chills the low-level air. So we've looked at this in the oceans. When you put warm water on top of cold water, it's stable. In this case, we're putting cold air underneath warmer air aloft, and that's called an inversion. Inversions suppress storms from forming. So even though you will have plenty of humidity, plenty of moisture in the air because the ocean's right there. That stuff can't rise up and form a cloud for long enough to form a nice precipitating storm. So all the ingredients are right there. They're just lacking that basic ingredient of lifting to create clouds, and that doesn't happen there hardly ever. So these zones, being closer to the ocean than inland deserts, certainly have less seasonal and diurnal ranges in temperature as a result of the moderating effect of the ocean. So this picture is looking down the Namib, the West African coast, also called the Skeleton Coast sometimes, and it really is kind of a juxtaposition of really high and dry dunes next to obviously a very moist ocean there. So those are the primary zones in the tropics. Let's think about some impacts that are happening right now. The Cauqueya ice cap in Peru at 18,000 feet above sea level. It's retreating at about 600 feet a year in many places. Many people downstream of this rely on this for drinking water. To give you an example of how fast this is happening, 1,600 years of ice in the Andes melted in just 25 years. So this looks at 1978 versus 2011 roughly. This is 1978, and you slide it over and see 2011, quite a difference there. Other tropical impacts from a Nature article in 2010 was called Global Metabolic Impacts of Recent Climate Warming, something people don't think about. A quote from the article here: small temperature changes can push tropical organisms beyond their optimal body temperatures and cause substantial stress, while organisms in temperate and polar regions can tolerate much larger increases because they already are used to large seasonal temperature swings. So if you're not used to changing temperatures by having seasonality, you are definitely prone to problems if global warming gets the temperatures up higher. That'll introduce tremendous stress, and that's what the article's about. Deforestation has several impacts on the environment. Of course, fires release CO2 and carbon monoxide. Carbon monoxide actually adds to create low-level ozone, which is a problem, certainly a pollutant down low. It's a very reactive molecule. It can react with your body and any type of wildlife or any type of biology, really. Smoke can inhibit cloud formation, thus influencing the radiation budget in many ways. Many studies have shown how smoke goes up over the Amazon. It warms that layer of the air up there, makes it warmer up there than it otherwise would be, and it actually can inhibit these clouds by that method. Deforestation can also change the surface energy budget. You take down a very moist rainforest, replace it with a savanna that's much more dry. Radiation that once went into evaporating water now just heats dry earth. In fact, many times it's been documented that these clear cuts actually are like kind of hot plates. And so you get moisture streaming in over the forest and the ocean. They go over these hot plates, and actually they're kind of a focal point for thunderstorm generation. So they are changing the weather patterns and the overall radiation budget too. Here's looking at causes of deforestation in the Brazilian Amazon from 2000 to 2005. And this hasn't changed much. Cattle ranching is the main problem down there as far as deforestation. When prices for beef are high globally, there's a demand, and it makes financial sense for many of the people to go out, clear-cut land so they can grow savanna, so they can grow cattle and make some money. So that's the biggest problem with deforestation down there. But it's a global problem because there's always demand for beef, and they'll respond to it. Now, logging is about 2 to 3%. That might have changed since then a little bit. Large-scale agriculture, as much as 10%. Small-scale agriculture, this would be small farms kind of digging in a root, making one crop for that area instead of large-scale farming. So those are the kind of distribution of what's happening with the deforestation rates down there and the pressures that are causing deforestation to occur. One of the hotbeds of what's happening in the tropics lately is the palm oil and peat industry. A good chunk of equatorial tropical peatlands have been drained, removed, or burned in order to grow and harvest palm oil. Palm oil is everywhere and used for a lot of things. About 50% of the stuff at your grocery store has palm oil in it. Tropical peatlands have gone from being a carbon sink, taking more carbon out of the atmosphere, to being a carbon source now. When the peatlands catch on fire, they're a huge carbon source. And so this happened in Borneo just a year or two ago, and it gave off as much CO2 emissions during those peat fires than all of China would in a whole year. This pie chart showing the world palm oil production in 2010, the demand is still increasing very quickly. So here's Indonesia as one of the primary producers. Malaysia's in there, is also a big hotbed. Key points for Chapter 16. As a whole, the tropics have the least amount of seasonal variability in temperature on Earth. This is due to the consistent overhead sun, the consistent day length, and the consistently high humidity values. The tropical rainfall variability is generally large and defines their seasons. For the most part, rainfall patterns shift with the position of the ITZZ and the associated descending branches of the Hadley cell. The different regions, you have the tropical wet, the rainforest, the very smallest seasonal temperature range. Due to insulating rainforest and the equatorial position, the ITC is overhead most of the year, leading to those consistent rains. Tropical monsoonal, pronounced wet period associated with the position of the ITZZ and seasonal wind shift and the proximity of the oceans as well. The geography tends to draw lots of moisture from the marine winds during that warm season when the monsoon shift happens. Tropical wet and dry, a pronounced dry period with good rains when the ITCZ draws near. These zones are associated with savannas and mass animal migrations. Because the dry period is so long, it can't support life and animals tend to migrate. The large inland subtropical deserts are associated always with the descending branch of the Hadley cell at roughly 30 degrees north or south. The coastal deserts have cold water upwind that stabilize the low-level air so they can't get storms even though they have plenty of moisture nearby.